Hi, my name is Jianshen. I'm going to present our work, Scale Out Edge Storage Systems with Embedded Storage Nodes to get better availability and cost efficiency at the same time. To help remember this idea, you can also call it the embedded storage at the edge. This is the work done with my colleagues, Matthew Leocari, Philip Kufeldt, and my advisor, Carlos Maltzahn. As the amount of data generated by edge devices increases, there will be more and more infrastructure deployed at the edge. However, maintaining a large amount of infrastructures is challenging. Whenever a hardware failure that need to be fixed at the remote site, the service provider would need to roll a truck to this site to get the problem fixed. However, the cost of truck rolls are expensive. Moreover, edge data centers usually suffer from various environmental limitations, including the stability of power, the available space, and the accessibility problems. All of these factors affect the cost of providing high data availability at the edge. In this talk, I'm going to show the benefit of embedded storage for the case of edge. Unlike traditional servers that use general purpose servers as the building blocks, embedded storage systems uses embedded storage devices. And you can think an embedded storage device as an Ethernet attached storage device integrated with some computing resources, or you can just think an embedded storage device as a computational storage device. The figure on the right shows an example of a device, this Ethernet SSD integrated with the MBWU over fabric interface. A general purpose server usually hosts multiple storage devices, and therefore, whenever a critical component in a server that fails, for example, the CPU or the memory module that fails, all the data that's stored in the server will immediately become unavailable, even though for all the devices in the servers are still in good state. On the other hand, for an embedded storage device, it could be much simpler and much cheaper than a general purpose server, and therefore building a storage systems that using embedded storage devices could enable us to provision more nodes under the same cost, space, and power restrictions. And our argument is the more independent failure domains a failure mechanism spans, the more available the data becomes. And to prove our argument, we create an analytical model to compare these two different types of storage systems. And the goal is to determine the availability of embedded storage relative to traditional servers. And then in our evaluation, we use a metric that's called relative benefit, which is defined by the possibility of data loss of the server-based storage system over the possibility of data loss of the embedded storage system. And whenever you see the relative benefit is greater than 1, that would mean the embedded storage is better in terms of the data availability. To compare these two different types of storage systems, we have some assumptions of system configurations, and the first one would be that we assume the units deployments are homogeneous, which means all the servers in the server-based storage system are having the same configurations, and on the other hand, all the devices in the embedded storage system are the same model. We also think that both of the storage systems have the same level of network redundancy and power redundancy, and therefore we don't need to consider the complexity of these two factors to our model. We also we assume that both of the systems use three-way replication using the copy set replication schema instead of the random replication schema, and we're going to explain why we choose the random replication instead of the other one in the next slide. Finally, we assume the independence of servers and storage devices, and therefore we use the Poisson distribution to model the possibility of hardware failures. And note that the copy set replication is not our work, but we use this schema in our evaluation. With three-way replication, when using random replication schema, even though for each data that's stored in the cluster would have 3 copies on 3 different data nodes, but because of 3 nodes are really packed, when a sufficient number of data chunks that's stored in the cluster, any combination of 3 nodes that fail simultaneously would be likely causing a data loss, and that is because each of the data node under this schema would have replicate set relationships with all of the other nodes. Well, when using the copies of replication, we can reduce the number of replica sets generated for the cluster. And for the example shown in the figure on the right, each of the node would have replica set relationship with at the most 2 of the other nodes, and therefore we can reduce the likelihood of the loss under a correlated failure with any combinations of 3 nodes. Besides the assumptions for system configurations, we also need the assumptions of system of model parameters, and I will go through all of the assumptions one by one. The first one requires that the failure rate of the non-storage components in a general purpose server will be equal to the failure rate of non-storage components in an embedded storage device, and would also have the same assumption for the storage component and the 2 different types of deployment units. Then we define the F, which is the ratio failure rate, and it is equal to the failure rate of a storage device and a general purpose server over the failure rate of the non-storage components in a general purpose server. And with F, we can bridge the failure rates between the 2 different types of resources in the same deployment unit. Then we have C, which is the ratio of computing performance, which is defined by the number of devices in the embedded storage system over the number of servers in the server-based storage system. Another way to understand the C would be that we're going to need C units of devices to get the same performance of a single server. Then we also require that the number of storage devices in server will be greater or equal to 2. And finally, we assume that will be at least 3 servers in the server storage systems because we're going to do 3-way replication. The reason that we define all of these parameters is that we want to evaluate how sensitive of the relative benefit to these different parameters. And with all of these parameters defined, we can evaluate. We now can define the analytical model. For the detailed mathematical expression of the model, you can refer to the paper. But in this presentation, I just want to show the evaluation results regarding the events of data loss caused by the failures of exactly 3 components. Of course, you can evaluate the failures based on different number of components. But in this presentation, just using 3 components as example. So when I say the failure of a component, it could be the failure of a server, or the failure of an embedded storage device, or it could even be the failure of a single storage device and a server. And so the way we are going to evaluate the relative benefit is that we're going to fix the first 2 parameters, which is F and W, and going to change the rest of the 3 parameters, and so that we can evaluate the relative benefit as a function of M and N, and as well as the relative benefit as a function of M and C. And so we found that the different storage media have a very different failure rate. For example, the failure rate of a spinning hard drive would be much higher than the failure rate of a solid state drive. And so in this example, we set F, which is equal to 2, to represent the failure rate of a spinning hard drive is twice of the failure rate of the non-storage components in the server. And on the left figure, it shows the impact of storage aggregation on the relative benefit. Take one of the label as example when we compare a server-based storage system that has 10 servers with the device-based storage system that has 40 devices, and the relative benefit is 7.1. And as you can see, when we increase the number of storage devices per server, which means each of a server would have higher storage aggregation, result would be a significant increment on the relative benefit. On the right figure shows the impacts of the compute aggregation on the relative benefit. In this case, when we compare the server-based system that has 10 servers with the embedded storage system that has 170 devices, the result would be the relative benefit would be more than 100. And as you can see, when we increase the ratio of computing performance, which means we're going to put more and more computing resources in a single server, the result would be a significant increment on the relative benefit as well. So in this case, we changed the value of F to describe a much lower failure rate of a solid state drive, and we look at the label at the same position, which we're going to compare the server-based system that has 10 servers with the device-based embedded storage system that has 40 devices. The relative result will be 20.7, which is much higher than the previous case when using the spinning media as the storage. To summarize what we found in the evaluation, we have the following 4 insights. The first one would be the higher the storage aggregation of a server, the higher the relative benefit of embedded storage. As you can see, no matter for which kind of storage media, the relative benefit will increase as the number of storage devices per server increases. The next one would be the lower the failure rate of a storage device, the higher the relative benefit of embedded storage. As you can see, the curve of the solid state drive would always goes above of the curve of the spinning media, and the only reason is that the failure rate of a solid state drive is much lower than the failure rate of a spinning hard drive. And the higher the compute aggregation of a server, the higher the relative benefit of embedded storage. And as you can see, no matter for which kind of storage media, as we're going to put more and more computing resources in a single server, the result will be another significant increment on the relative benefit of using embedded storage as well. And finally, which is sort of an emphasis on the impacts of resource aggregation on the relative benefit. Specifically, on the left, the figure shows when we double the storage aggregation of a server, the result would be a 3 times increment on the relative benefit. On the right figure, it shows when we double the compute aggregation of a server, the result would be a 4 times increment on the relative benefit. Now I can conclude my talk. The reason embedded storage devices can provide higher data availability is that they are simpler and cheaper, and that would enable us to provision more nodes under the same cost, power, and space restriction. Building storage systems with embedded storage devices is a great design point, but there are still many unresolved challenges. One of that would be how to balance the availability and performance, given that each of the embedded device could be much lower performant than a general purpose server. So thank you very much for listening to my presentation, and I'm ready to take questions.